Today I want to shift a little bit toward deploying models, and which is a little bit more of an architecture and design discussion. I want to start by essentially telling you deploying a model is easy. A bunch of you have already done this for this milestone and probably maybe in other places. Right? So you can just, a basic strategy is have a model, serialize this as a file, as a pickle file or something somewhere, and then in your code, when you need to make a prediction, load that model and just call the predict function on that model, or whatever your library does. Right? Deploying a model is trivial in a way. You just have a library that can load these files and make predictions. If we want to make predictions over the internet, like you might want to do for the homework and for lots of other tasks, it's very easy these days to create a web service that you can just query. Here's an example of get objects. It's a post method, so you can call this with curl at the address with get objects. Provide, in this case, a file. There's a little bit of configuration of where to upload the files to. And then inside this thing, again, we just have our model, which we load, again, with Flask or something else, like it was pickled. We probably don't want to train this in the same process, so we probably pickled it, load it, and make predictions and return the predictions over this. I assume I'm not telling you really anything new. Right? Again, deploying models is really straightforward, and if we don't like this, we can also put it in a Docker container and make this easier to deploy on a different machine, that we don't have to install all the Python dependencies. We show you a little bit of Docker still in the lab this week. But I assume at this point you've seen at least conceptually what Docker does. Probably a lot of you have used it in some form. Right? You're going to use it for the project too. I think it's only mandatory at milestone 3, but you can start using it earlier. Might be useful. It handles a lot of dependencies. So this is essentially the same. You have a container. In this case, we put the pickled model file into the container. So we ship the container with the model fixed in there. We could also load the model as a volume from a different resource. Right? Then we have the Python code, maybe what I've just shown you here. Right? This kind of code to start a web server. We expose this. We run the web server in some form in the container. We can deploy it somewhere. And these days, you actually don't even have to write any code to do this. Claire showed this picture last time of the small black piece of machine learning code and then all the infrastructure code around it, kind of an old MLOps picture. These days, there wasn't even what I've shown you that much code to deploy things. But even that, we don't necessarily need to write. We have all these libraries, and this keeps changing. There are more of them that essentially take your pickle file and turn it with a little bit of configuration, with like a YAML file or something, into a deployable container, and maybe has even some functionality to scale it. Right? So these are low-code service creation or deployment things. They often integrate with other services, like registering your model somewhere with auto-scaling in the cloud. So if you want, you don't necessarily have to write any of these codes yourself. The problem, if you're going this route, is you need to understand how to use those libraries and which one to pick. So there's complexity in a different place, but once you know how to use them, there's a lot of things. AWS is happy to sell you stateless serving functions as put your container in there and they will serve it to as many clients as you want, as long as you give them a credit card. Right? So if you have more requests than a single machine can handle, they will happily scale it for you on 10 machines, 100 machines, 1,000 machines. You might want to set a credit card limit, but in theory, they will do all the scaling for you if you want it, if you trust it, if you give them enough money for it. Right? So in a way, solved problem, model deployment, really straightforward these days? In a way, yes, but the complexity comes from specific use cases and what are you doing specifically. Are there cases where you need to deploy a model offline? Then AWS auto-scaling is probably not the way to go. Do you need to deploy at scale? Then don't run it on your machine or have it in the application. Right? Do you need specific hardware? I mean, we're all talking LLMs these days, which is all GPU-based. Not all models are that hardware hungry, but modern models often are, right? Do you need to ever update the model? Then having the model in the container is maybe not the best solution because you're replacing the container and uploading everything and deploying this everywhere. And in a way, every system is different, and we need to figure out how are we designing the deployment for a specific system. I want to collect with you a couple of qualities or things that we might worry about when we're deploying models. And I think we talked about some of them implicitly. But what are some of the things, if we're deploying a model, what are we after? What kind of quality? What kind of service level guarantees might we want to provide? What might a user of our model want from our deployment? Low latency, yep. We might care about latency. Let me take some notes. What else? Scalability. Like many concurrent requests, or another way of scaling? What do you mean by scalability? Handling many requests concurrently? Okay. Yep. Availability would be the common term for this. Availability. Close enough. What does maintainability mean for you here if you're deploying a model? Yeah. Yeah. Something like this, right? We want it easy to update or replace it with a new model, switch over in some way. And then again, combine this with availability. If you switch over to a new model, don't take it down for an hour in production. What's a failure? Low rate of failure? Right, so kind of in traditional software, this might be the software should not crash. We don't want those failure cases. This doesn't happen that often with machine learning code because we're just doing a bunch of matrix multiplications, right? The non-ML code is usually not very complex. Maybe there's a bug somewhere in here or handling like I/O, upload, image loading, and we want that to be robust. But the inference function for the model, that doesn't typically crash. Or at least I wouldn't expect it to, because it's just matrix multiplications, right? So there's not really coding bugs. But how do I write this? Robustness, maybe in some form. If you get weird inputs here, right, you don't want to crash from that. Or isolate mistakes in some way. Anything else? Predictability, yeah. I'm not quite sure how to fit this in, but yes. So let me give you a couple of scenarios, mostly things that we've talked about, where you might want to deploy a model, and think about how you would deploy it. What are the kind of differences that you might want in some cases, but not in other cases? What are qualities that are sometimes important, but maybe not in all of these cases? Is scalability equally important in all of these? Right, so we have a bunch of these. Scalability, this is pretty predictable how many requests we get, right? This doesn't need to scale massively if you're running it on the phones themselves. Latency, I think we have very different requirements. Some of them, this we can run overnight before. This we can probably wait a couple of minutes. This we need a prediction right now, whether there's an obstacle, right? This is a real-time use. Is there anything beyond the ones that we covered that might be different for these? Security? Of what data?
Maybe like training data or using data.
Right, so We'll talk about security more later, not in this lecture. Training data might not be in the model, or not. We don't deploy the training data typically. We deploy the trained model. But even there, do you have access to the model file itself? How easily is this possible to access, right? You can always steal models, but you can make it more expensive for somebody to steal a model. Anything else any other qualities or differences that we might care about? How much of an internet connection do we need for these kind of things? Could we always just deploy this as a serverless function at AWS? If the train goes into a tunnel, do you want your smart keyboard to stop working when you don't have internet or Wi-Fi, right? So there's maybe sometimes you need offline deployments, right? Here you want some federated training, probably. This might not be one model. This is probably multiple models, right? So you have things that work together, like the lyrics generation and then the music generation as separate things. So the point that I'm trying to make is pretty much what's on the slide. Every system is different. Yes, we have patterns of how do we deploy models, and the basic deployment step is easy. But once you get into the weeds and figuring out, I need to deploy a model for this system in this context, you actually have a lot of design decisions and trade-offs. And you might want to think about how to deploy a model in a way that works for the application and that's also cost-effective and meets other qualities as well. I want you to think through one use case that's a little bit more nuanced about deployment questions. Do you know where this picture is?
Korea.
Yep. I have no idea. I can't read this, right? So for me, it would be really useful to have something that would translate this for me. It's not the most novel technology, right? But you probably all have seen like the video mode in Google Translate or similar systems where you hold the camera on something. But that's boring. Let's go a step further and say we're walking. Maybe not these. We're walking around with smart glasses and can do some augmented reality kind of thing. Not particularly, personally, I'm not super interested in virtual reality, but augmented reality like this, something subtle, right? Whether it's the new Meta Ray-Ban glasses or something. I don't think they have a camera on that, like a projection on them, right? The old Google ones had. Nobody wanted to be a douche running around with those, but I mean, if I go to Korea and I want to actually see things and it would automatically translate for me in my vision, like overlay this similar to this, I wouldn't mind. That sounds like a cool product to me and something that I would actually care about. Right, so let's think about how we would build something like this. I assume the glasses themselves don't have enough computational power to deploy the models that we need. What kind of functionality do we need? Let's assume we have a camera. We need some sort of text recognition first from the image, right? Some sort of OCR component. Then some sort of translation of that. And then maybe we want to do this every frame, but probably some sort of image stabilization, like if we move our head, that the text moves with this to some degree. So we can think about having at least 3 models here: OCR, translation, and some sort of motion tracking. They're of different size, different difficulty. It's not the most challenging. We're not deploying LLMs here necessarily. And we can think about where do we deploy this. We have the smart glasses that have a camera and a display, are battery powered, probably not the strongest CPU, probably no GPU. We have a mobile phone. If you want, we could think about something more powerful with an AI chip on them, if you think so, but still battery powered. And you have some cloud infrastructure where you could also host something, because these things are typically, your phone is often online, so it could send requests for translation to the cloud. So where should these models live and why? We probably need to think about some qualities, like Can we send data over the network connection? How fast does the response time need to be? And I would like you, as a breakout discussion now, to have a discussion about where these things should live. And I would like you to actually do some research to figure out what's realistic here. I assume most of you don't know what bandwidth Bluetooth can provide, or what would be needed for video streaming, or how fast a translation model is, or how big a translation model is. So do a little bit of Googling and figure out what could you deploy where, what seems realistic, what are constraints, and think about where these three models should live, right? So think about latency, bandwidth requirements, discuss trade-offs, where should which one be, and I would like you to tell me where would you recommend OCR to live, and give me a justification why on that. Those are your main three options if you can think of something else. And tell me where the translation component should live. Clear? Go. Okay. A bunch of you responded much faster than I expected. I would say this is actually not that of a straightforward decision. What were you talking about? Claire, do you want to pick a volunteer?
So we were basically talking about...
He already got chocolate today.
Oh, I haven't yet.
Oh, you haven't, sorry. Bad memory.
But we were basically saying that OCR and translation are ones that would need to be a little bit faster or with lower latency, so they should be on device, or so on the smartphone at the very least. And then, well, more so the OCR portion. The translation was an interesting one because I think that's a little bit we think it's a little bit more likely to update and change as well as more like languages are supported or translation techniques are.
So you're thinking about how stable these things are, how often you need to update things?
Right.
How quickly is Korean evolving as a language?
Mainly we're talking about like different languages.
Okay, no, it's fair, but it's probably not several updates a day, right? Which is an argument that you don't want to download this regularly. Are people using Google Translate in offline mode? You can download models, and they don't push updates that often, but
yeah, but
that's fine.
Like, let's say we have different languages, but you cannot have them all on yourself, like on device.
Yep.
But if you happen to encounter something, I don't know, in Chinese, and you don't have that, so you have the option to get access to that, but through the cloud, probably.
Okay, I think that's fair. So you can argue that maybe if you just need one language, you could download this, right? But if you want it to be flexible, you probably don't want to download translation dictionaries or models for all possible languages, yeah?
So like how often are you running into like that live translation of 6 different languages? Like you're in China, you're in Korea, so everything's going to be in Korean.
But if you're reading some like research and then you find something in like Chinese, that'd be useful.
For modes where I'm not traveling, right?
Yeah.
Right?
Good to have a variety.
Has somebody talked about whether bandwidth is enough for doing OCR on the phone?
Bandwidth for Bluetooth is around 2 to 3 Mbps, so live streaming for videos is not possible. And after we do the research, the OCR models for edge devices could be shrunk to around 0.9 billion parameters, so it might be feasible that we put the OCR on glasses.
Okay, so you think there might be very small OCR models that could work on glasses, right? I think when I looked this up a while ago, the bandwidth would be okay for low quality video streaming, or medium quality video streaming is kind of at the border what Bluetooth could do. Not sure that low quality video is really what you want to run OCR on.
think. I think the finding like sweet spot is very good because I definitely like using cloud infrastructure would be very good for the quality of the outcome, but it goes to like 2 layers, like using mobile phone, Bluetooth, and 4G layers. So I think finding using like smart glasses between glasses would be very like finding between them would be a very good option too. And thank you.
Has anybody talked about whether you actually need video streaming? Thanks. Okay.
You could have maybe a lightweight model that can segment the maybe looks like text of some language into a smaller, much smaller resolution area. Also for privacy, because you don't want everything else that's not text.
Yep. Don't OCR the entire image, but segment it first, and then this is. Yep.
It made you nervous. That was the problem.
It's the less aerodynamic chocolate. Are there alternatives to streaming?
I don't know how they usually work, but I feel like it could be a sort of on-demand feature. So it's like maybe you're looking at it and just like click a button or something and say, okay, I want a prediction like on this, and that way you're only getting like one image or a few frames rather than like live stream video.
I also assume you wouldn't really want a translation for every single frame independently, and you don't really have new text coming into frame, in and out of frame, in every single frame as you're moving along. Right? So I suspect you can actually do a lot with still photos or just do one photo a second or something like this. Right? I think doing some motion tracking to actually see what's stable, what's moving around might be really important to not have things flicker. You also don't want a different translation for the same text in every single second or image. Have you looked into latency? Like, what kind of latency would you need for live translation for augmented reality? I looked this up a while ago. 200 milliseconds is a noticeable speech delay. So this is a kind of thing when you have 200 millisecond delay over a phone conversation, then you fall into each other's words and interrupt each other accidentally all the time because there's this weird lag. For video, you notice it up to 20 milliseconds. It's really weird when video and sound is slightly off, right? So it's a very short amount of time. So you need a very quick latency if you want to be faster than that. Haptic feedback is even faster, 10 milliseconds. People talk about cyber sickness. If you have virtual reality and it doesn't move fast enough, people get sick from this. It's again 20 milliseconds. So that's about your latency that you would need, at least for image stability tracking. You probably don't need the translation in that speed, right? The translation can come later, but you don't want it to flicker constantly. So I think I didn't ask you about the motion tracking, but I would expect a typical system to do some sort of motion tracking to just move the text when you're moving your head. That needs to be extremely fast. The translation, probably not so fast. If you're looking at a sign for 2 seconds until it translates, I suspect that's fine. So you could probably live with internet latency. But you also might want to think about whether it should work offline, right? Does it need to work without the phone? Maybe less so, right? Maybe you can rely on the phone connection, but maybe not on an internet connection. I don't think there's a single right answer, and I don't think we can answer this right now what the best design is. It depends a lot on what model you have, what kind of requirements your users have, what kind of design decisions you can make of maybe not analyzing every single frame, but analyzing individual photos, maybe compensating with image stabilization instead of doing OCR over and over again. The point that I was trying to make is that this is far from trivial, right? We really have non-trivial design decisions here, thinking about how do we deploy things, where do we want to move things, and we can make different designs if we can get a model to behave in a different way, right? If we can get a smaller model, maybe we get away with putting it on the glasses, right? Or have a hybrid combination where we have maybe a quick translation model on the glasses and a better one in the cloud, and use a better one if it's available. This is a kind of, and we haven't even talked about energy consumption, right? How big the models are, how much energy they're consuming. This is the kind of design decision that's pretty common and that's often thought of as architectural thinking. Architectural thinking are the key design decisions, software architecture are the key design decisions that are hard to change later. Things like, how do I deploy this in a completely different way? What latency do I need to get right? What are the key qualities and what are the key design decisions to get them right? I'm going to step back for a second. Architectural reasoning typically has a lot to do with abstraction. In our discussion right now, we were kind of meandering on a bunch of topics, but we thought about latency, we thought about bandwidth, and so on. And that's a common way of reducing complexity to a problem. A way to explain architectural reasoning that I stole from a colleague that I like is this. What do you see in this picture? Not a trick question. It's not Pittsburgh. It's a map of Pittsburgh. The distinction will become important in a second. What do you see in this picture? It's a terrain map of Pittsburgh or a bicycle map. When would you use this map rather than the other one? When you're bicycling, yeah. If you want to avoid deep valleys, if you want to know where the bike roads are, bike lanes. Any idea what this is?
Like a fire map for like different fire response times.
Yeah, different fire zones in Pittsburgh. Which fire station is responsible for which location? Who might care about this? The fire department, yeah. Claire, as a homeowner, do you care about this?
I do, because at the annual block party, you can call the fire station, and they will send a fire truck to your block party so that your kids can climb into it. And so it is relevant what fire block.
All right, good. So maybe it's very obvious. These are all three different representations of the same underlying system, real-world entity. And each of these representation is necessarily an abstraction that we're building. Right? It's not representing all of Pittsburgh. This one isn't showing bike lanes, the other one is. This one isn't showing fire zones, the other one is. None of these are showing addresses or buildings or all kinds of other information. Right? They're always abstractions to a degree that we can reason about them. And each of these abstractions has a specific purpose. We can reason about some purposes with some abstractions and not with others. What we're doing, again, maybe a fairly obvious point, but we're abstracting a real-world entity for a purpose that we want to reason about up to the point that we have all the information that we need for that purpose and none of the distractions for something else. And in software, we see all kinds of diagrams of real-world systems, often sketched, often informal, that have a similar purpose. And so this is a way to think about a system that's extremely abstract. It's some inventory management shipping system where people can order things. We ship something. There's some IT system. It doesn't really tell us anything about what the system does in detail. But what might this abstraction be useful for? So similar to showing you a bike map, what is this map useful for? What might this be useful for? What might a software engineer or designer use this kind of information, this kind of abstraction for? Or is it completely useless to draw something like this? Yeah. So you could see at least who's involved. I don't think it's the right thing to understand the ordering process, really. You can see a little bit of who's involved, maybe. What else could you reason about? Why might a software developer care about an abstraction like this?
What parts of the component can the software developer control, and what are the parts that are out of his control?
So what can the software developer control and what can't they control? Why would you care about this? Sorry.
To think about how you can develop later and to...
Okay, to think about what you develop now versus later, although there's just one system that we're developing. Why else might we care about what's under our control and what isn't?
Well, there's a box that says LAN, so you can track data flows, what's inside your network without security.
Yep. So security is a common thing. At least it gives us some idea of how data flows. And if we trust our internal systems, the people who do shipping or IT may not need extra accounts or encrypted connections here, but these connections go to the outside world. So these kind of diagrams that show you the network and where people are might inform decisions about where you add encryption, where you add two-factor authentication, extra passwords, things like this. This is a diagram of Google file system. This is a massive storage solution where you can store huge amounts of files. There's the idea that you have the central server that essentially just stores where stuff is. It's just an index. And then you have the chunk servers that store the actual data. You can see with this diagram a couple of things. A, that chunks are replicated, that there's only little information here. The data is at all these different devices. You see this extra big line here that indicates this is where all the data goes. Google file system is designed to download massive amounts of data in parallel from many chunk servers. But the central server is not the bottleneck, right? Because we're just using this for lookup, this connection here where we look up where the chunks are has relatively little traffic compared to downloading this from the rest. So the specific details don't matter too much. The point here is that we're using these diagrams similar to how we use maps of a city for specific reasoning. If I want to care about reason about security, I would maybe use something like this, not something like this. If I think about latency and where my bottlenecks are in the system, this might not be the best abstraction here. And in this case here, I've shown you this diagram. It's a very simple abstractions of just what the devices are, and I can start reasoning about what the connections are. I've shown you this diagram, which is also an abstraction that focuses on specific reasoning, right? What's the latency? What's the throughput? These kind of abstractions are often useful. We often do some research focused on specific qualities that we care about. Right? Previously, we cared about where do we place a model to have sufficient latency to be able to handle the amount of data. So starting to reason, whether you do this as a graphical model or not, starting to reasoning about the relevant abstractions and do this before you build the system in an early design phase is really useful. Any questions so far? We're not going to make you draw silly diagrams just because, but in your design of the group project or other systems, you might want to think about, is there something useful that you can use to visualize? Are there things that you're prioritizing as you build the thing, for example, to be high availability or high throughput or low latency? It might be worth thinking about where are the bottlenecks and draw that as a diagram or even if it's text, right? Identify the right things and ignore all the rest of the system. And for a typical system, you may have many different diagrams for different purposes. One more thing that people who do software design and software architecture do a lot is try to codify common knowledge as patterns. I suspect most of you have seen design patterns as somewhere in your degree, as an undergrad somewhere. What's the observer pattern? I guess it's on the slide. What's the strategy pattern? Let me pick a different one. Does somebody remember this? Who here has no idea what I'm talking about? Okay, some. I assume the rest knows precisely what these things are. Can somebody try to explain one of these patterns or explain what a design pattern is?
I mean, one of them is literally on the slide.
I know.
So you could just, I'm suggesting to the class that they could just read the words aloud and get some chocolate.
Yeah, I mean, there's many other design patterns, but those are the most commonly taught ones. So design pattern is a common strategy to a common design solution. The observer pattern is relatively low level in code. If you have two classes, two objects, and one of these objects needs to be notified whenever something changes in the other, it's relatively easy when the first object has a reference to the other and just calls every time that they make a change. But that means that the first object needs to know what the second object is. And that's often seen as tight coupling. That's a bad idea. Right? So if you think of an application that every time a button gets clicked needs to do something, you don't want to hard code when you implement a graphical user interface for a button what action happens then. So rather, the idea here of the observer pattern is that you decouple these things and you have a callback mechanism. So if you've ever used GUI programming, there's always a add listener function or something like this, right? Or notify me, on call, on click, do something. That's what's described in the observer pattern. You have a way to, the button is always the same, but you have a way to register a callback function if an event happens, so that you can register, I want to always be informed if something changes here. Right? Buttons are the obvious things, but you can also do this for all kinds of other computations. So you have a database, and every time something changes in the database, you want to be informed because you want to update something. Right? There are mechanisms for this. This idea is so common, this kind of callback mechanism for being notified about things, that we don't want to reinvent this all the time. So an observer pattern has, or a design pattern often has some notation of what are the abstract entities involved. There's a publisher and a subscriber. There's a subscribe method and a notify method and some descriptions of how this would typically look. This is not a library that you would reuse. This is not function code that you reuse. This is a design process or design idea. And you can just re-implement this in many different contexts. So there's some description. You can get a book on design patterns. This is actually quite commonly taught. I've taught this many times. Claire's taught this many times in other classes. Common design solutions that help you to abstract more and solve common problems in the code and write better code that's better decoupled. The power from design patterns comes from cataloging these things and giving them names so that we can talk about at a higher level of abstraction. Maybe we should decouple these things by using an observer pattern, rather than saying, maybe we should decouple these things by maybe create a callback function and have a register method, and then you can just register yourself and get it notified later. Right? So you just describe things in higher levels, in concepts that carry a lot of knowledge with it. And this idea of codified knowledge, whether you call it pattern or something else, carries through to all kinds of other things. I'm sure you have seen these kind of things discussed, right? Client-server, multi-tier architectures, service-oriented architectures and microservices, which I somehow have twice in there, event-based architectures. Maybe not everybody has seen all of these, but they usually come with connotations. This is a microservice architecture. We'll talk about this later a little bit. Microservices are the idea that you break down functionality into independently developable services that are usually called over the network. And they're microservices because the functionality is very small. This is something like Audible might look inside, like an audiobook service where you have maybe a content delivery engine that has only the functionality of serving you the audio files, and then you have a content delivery service that knows to manage these things, have ownership records, and so on. So rather than having all of this in a single application, you break it down. And these could be all things that are separately deployed over the internet. This could be written in Node, this could be written in Java, this could be written in Python, deployed separately, each in a container, and then you distribute this over the internet. And benefits of these are that you can replicate them independently. So if the cache needs way more servers to run this, you don't need to replicate the entire application, right? So again, I don't want this to become a lecture on design patterns or microservices. The idea here is just that we have common patterns, and knowing them will help us to communicate common design trade-offs and common ideas more easily. When it comes to machine learning, we're starting to recognize common designs and trade-offs. There's not a huge, well-defined catalog. People try this. But these are common patterns for how you deploy systems. I think maybe the most obvious ones are static intelligence in the product. This is the offline deployment. You bake it into the product, essentially. Client-side, and then you can never change it. Client-side delivery intelligence, it's on the user device, maybe on your phone. You can probably have a download mechanism or update mechanism. Server-centric, this is, I think, what you expect by default, deploying this in the cloud. Back-end cached is something where you pre-compute a lot of things. You have a lot of very similar queries, and you see whether you made the prediction before in the past. So some sort of caching. Maybe not that relevant in LLM days, but in the past we had a lot of predictions where the input domain is maybe relatively small, or very common things, maybe lots of words that are commonly translated, right? So you can cache a lot of those. And then hybrids of those. And again, I think the trade-offs for a number of these are pretty obvious. Like if you want to use it offline, you only can use the first two, really, right? The rest requires internet. If you care about latency, less network latency is probably a good thing. So the offline ones will benefit. This one is also can be really low latency because you're not making actual predictions most of the time. But sometimes the model latency might be worse than the network latency. So in those cases, it might actually be better to deploy it in the cloud on a more powerful machine than trying to run an LLM on your phone. Right? Model updates, if it's in the cloud, it's much easier to update. You don't even have to tell them. If it's on your phone and you have to send update notifications or download a large model once a day, your users get grumpy, probably. Operating costs, I think, is an interesting one. Who pays for the electricity to run model inference? If it's in the cloud, it's you. And you need to monetize this in some way, kind of get the money back, right? If you push it out on the user's machine, if you do some sort of prediction in the browser, it's running on the user's machine, right? So you don't pay the electricity for that. So I think this is pretty obvious, so I'm not going to cover this in much detail. Do you have any questions? I think we could go back and contrast it against the qualities that we did earlier. I guess we covered most of these. For scalability, if you need true scalability, what's a good design? Which one would you pick? Server side? This means you can just add more servers and more servers. It's also expensive. If every client brings their own device, it's pretty scalable, right? It's running entirely on their machines. Like if you have twice the number of clients, you have twice the number of machines to run this. So it's kind of inherently scalable in that way without extra cost. Security? Depends what kind of security. Let's say the model, we don't want them to leak the model weights. You kind of have to run it on a server, right? If you put it on the client machine, like if you put it in the binary of a mobile phone app or in the web browser, this is essentially leaked, right? You can reverse engineer that. Okay, wrong. No. Okay. Couple of other things that people talk about. You might see, again, maybe less common these days, but we used to do a lot of feature encoding, lots of data preparation. And even if you run the model in the cloud, you can think about where do you deploy the feature encoding. So in a way, the OCR component was kind of a feature component for the translation thing. Maybe a bad analogy, but often you do a lot of processing of like input data to then get a feature vector, which you use as input. You can do this on the client. If the feature vector is much smaller than the original data, then this might be efficient to reduce network traffic. What's a drawback of doing this on the client side? Have you heard of training testing skew? What if your feature encoding ever changes? You use a different embedding for some input data for the model, right? You can update the model. It now expects a different embedding, but you need to update every single client. If a single client is on the old version, you either need a way to detect this or you just get an embedding that doesn't make sense, right? And models are usually pretty good to give you a prediction anyway. It's just not particularly reliable necessarily, and it doesn't give you an error. Right, so this is a pretty common trade-off here of do you do feature encoding on the server or on the client? There are trade-offs for both of these, but really having them drift apart, having the feature encoding that you use during training be different from the one that you're using at runtime is really dangerous. So you need to think about how do you do this if you deploy them in different sites. Right, if the training is run somewhere differently. Somebody seen the feature store? What's a feature store? I see some people nodding.
Single repository that we store all the features, like usually in an organization, like so that there's no replication of features.
Right. Yeah, so if you have feature, that was really bad. If you have feature engineering code and you invested a lot of effort in doing this, like the conversion of download counts or trying to estimate somebody's zip code if the information isn't provided, like some non-trivial feature engineering code, there might be multiple teams in a company that might benefit from having access to the same thing. And traditionally, it was very common for people to just redundantly re-implement the same encoding over and over again. Feature stores try to solve that pattern by taking essentially these small code snippets that you use for feature engineering and sharing them within the company as a catalog. So I have a feature for X, I have a feature for zip code, I have a feature for income or something like this. Some of them might be quite expensive to compute. Some of them might use a different model, like predicting somebody's income if we don't have the data. So feature stores also often cache the data. But again, this is a pattern, a central place to store and version the code for feature engineering. To cache feature values potentially, there's a couple of tools. Again, since we're moving, or the hype is moving toward LLMs, we're doing less feature engineering, so this hype has died down. But I think if you're still doing tabular data or any traditional machine learning code, this might still come up. And I think this is still relevant in a lot of organizations that do a lot with customer data and all kinds of more traditional data science things. There's a couple of patterns that are maybe a bit more machine learning specific that people sometimes talk about. I think the thing that people agree more on are anti-patterns, things that you shouldn't do. And some of them are funny. I think mostly self-explanatory. Like if you have a lot of glue code in there, that's kind of not maintainable, right? Multiple languages tied together, maybe not the most maintainable pipeline jungles. You just call 1,000 shell scripts that you can't maintain. Last thing I at least want to briefly talk about is, Claire mentioned already last lecture that we're often, these pipelines, they're pipelines for training, but also pipeline at inference, more complex systems where we don't just have a single model, but multiple models and non-model parts together at inference time. Let me jump to this, right? You see things like this, and if you deploy models, you need to deploy sometimes multiple models in a way. Ensemble models, you probably also know as often this happens in learning, where you have multiple models and then you average out the results. There's a meta model or model stacking, where you have multiple models compute independently a result, and this model picks which model to trust. It's kind of similar to this, but it's not just the average. There's a little bit more intelligence in the second model. I think some sort of sequential composition is quite common. You see this these days with LLMs and dedicated prompts. This is earlier. This is how people used to do image captioning for a while, to decompose it into smaller models that do more things that we can understand a little bit more and test a little bit more independently. So for a while, the best image captioning models were doing something like this. First, object detection, like what are the objects in an image? Then have a language model, which by today's standards would be a tiny language model that just takes the objects and creates plausible sentences. And then there's some component that I don't understand that takes the image and the proposed sentences and ranks them in some form, right? Which of these sentences describes the image in the best way? What's happening here is that we're decomposing this into more easily definable things that we can develop models for. Like object detection is a very common problem. Lots of benchmarks, models that have been trained on this, so we can just reuse this out of the box. Language models, doing them separately, like some sort of real-world understanding, training them to create plausible captions that are just plausible English sentences based on a couple of keywords, is easier than going directly from an image to a sentence. Right? So this kind of decomposition sequentially is quite common. And we're doing this also, I think, a lot with LLMs. So this is a way that the autograder or the auto feedback mechanism for the breakout session works. I have a prompt first that checks, does this have anything to do with the breakout task, or is this a different message? And if it has anything to do, here's a list of criteria to check against. And then there's a second prompt that tries to give me a concise and friendly, doesn't always work, but friendly feedback message. Neither concise nor friendly always works, but that's the intention. Trying to do this in a single prompt was just not getting me anywhere. Doing this in multiple steps helps a lot, because the first thing, the first model or the first prompt can focus on critiquing it, and the second prompt can focus on creating an acceptable feedback message in some form, right? And you can tune them somewhat independently, right? So decomposing things into multiple steps is a common pattern. Another way of using this was, by the way, called cascading or two-phase predictions, is combine a small model and a big model. Something like Amazon Alexa works like this, where there's a small model just looking for the keyword, the activation keyword, and then you have a big model to analyze the text that comes afterward. This is an example of detecting what instruments are in an audio file. I don't know why. The first one just detects, is there an instrument at all? And only if there is, then you send it to the larger model to do the more expensive analysis. Right, so these kind of compositions, I think there's lots of flexibility, lots of ideas. These days, I guess Claire talked about this too, RAG is a very common way of having another retriever model in there, another search mechanism to generate additional context. You can also have all kinds of non-ML context engineering things. There's a lot of optimization too, like optimize prompts in your pipeline independently. And agents is essentially just adding a control loop on top of that that's decided by another LLM, right, where the agent decides, should I call a tool, should I respond immediately, call the tool, feed it back into the context. We're doing more of this later, but the key point here is, I started this lecture by saying deploying models is easy, right? And I think it is for the most part. Except when it isn't, right? Except if you're trying to meet specific quality goals, like these, right? You have specific requirements in your application where you need to achieve something. You have more complex pipelines where you actually want to trade off multiple models. You need to think about, do I deploy something locally, something remotely? Does it need to massively scale? Do I need agents? Do I need the flexibility that comes with it, with tool use, or do I want something more constrained? All right, I'm going to talk about this. You're all going to ignore me. And I know, but I'm still going to talk about this. How do you document models? Has anybody tried to release a model and document it for people who are using the model? Has anybody ever written a model card? How was that experience? Made some stuff up, yeah. So in an ideal world, we would like to document this, just like we document code. We would like to describe, hey, we build a model, and maybe an API to use that model. Here's you user as a model, here's how you use it. Here's what you can expect from the model. Here's what the model can do, what it was trained on, maybe what it supports, what it doesn't. Right? There's all kinds of people who didn't develop the model, who are using the model and would like to know something about it. In traditional code, we have classic API documentation. It's mostly crap, probably. Although if you're using libraries, some people pride themselves in documentation. In some organizations, maybe there's more emphasis. Maybe these days, models are good at writing this documentation. But it's something that we hope there is, and that's useful if we have some documentation. For models, it's often good luck. Here's a model. Best case scenario, we get something like this, which is the schema of how you call the model. Doesn't really tell me anything about what the model does. It just tells me what is the input or the output. Like, this is an object detection model, so it gets me bounding boxes and scores of different detected things in an array of them. So this is there that I can read the feedback, the JSON, whatever comes back, that I know what to expect. But that's the equivalent of the input and output types in traditional code. It doesn't tell me what it does, right? So this kind of documentation is missing. We would like to document all kinds of, we would like to have documentation about all kinds of other things. Probably wouldn't like to write this documentation, but consume it maybe sometimes, right? Those are all common things, like what's the intended use case, what's the model capable of, how was it tested, what's the target distribution, like what inputs is it supposed to handle, which ones isn't, right? What kind of accuracy maybe, what kind of latency should I expect? It's useful if you use an off-the-shelf model for translation, for example. Is it explainable? Is it robust? Is it calibrated? And probably also ethical considerations. Model cards are our best attempt at documenting models beyond just input-output formats. It's a proposal that came out of Google, originally intended as, I think, under push fairness considerations and think about those things a little bit more explicitly. This is a template from that paper that describes how a model card might look like, model details, intended use, metrics, ethical considerations, what training data, what evaluation data was used. There are a couple of good examples. Like Google has a couple of flagship examples of how you can nicely document models. If you look at their object detection models, they're nicely documented on the internet of what is this intended to do. Like if the object is too small, if it's less than 1% of an image, we don't try to detect it. Those kind of functional descriptions. In general, I would say there's almost no good documentation beyond a few examples. We did some research a few years ago, and there was certainly way more citations to the model card paper than there were model cards out there. And then Hugging Face started naming all their READMEs model card. So on Hugging Face, you now see model card over everything, but it's just a README file that's not systematically describing anything. So I think in general, we're not very good at documenting models. I can tell you this, and I suspect you're not going to get much better. And don't worry, I'm not going to make you write a model card for your recommendation service either. But I think it's worth thinking about what would we describe in documentation. And inside organizations, some teams care about this because you have this communication problem, right? If you deploy a model, you might want to tell the team what operational support do you give, what latency do you want to achieve, and also what can this model do and what is it not intended to do, right? So describing these kind of things is actually a useful thing, but it's one of those things where I keep talking about that we should do this, and I'm not sure that I can convince you sufficiently to actually go out there and just write documentation. All right. Again, I think this is what I wanted to convey today. Deploying models is really easy until it isn't, right? And a little bit of architecture thinking about what are the main qualities that we want to achieve, right? Do we care about latency or throughput or energy consumption? If you care about these things, plan these early. These are hard to fix later. And think about what are your choices, how can you deploy them, where should you deploy them? See you Monday.